Sorry for the delay. As you can see in the title, I'll be talking about the realization of what is called the Miura operators as R matrices of certain quantum group. So Miura operator is a notion that appears in the free field of realization you actually have seen already in the previous talk. And R matrices that you know are some objects, they intertwine some modules of the quantum groups. And what's surprising is that the former can be realized as a certain type of the letter A. And I'm going to do this by embedding this, these two objects, some vertex algebra pre-field realization of it, and the quantum group into some M-theory setup. So there are going to be some branes inside the M-theory, and they're going to intersect. And so this serves as an ideal example why mathematical physics can lead to, or at least motivate, the new statements in the math. So let me begin by introducing the Miura transformation of W algebras. The W algebra of type GLN is the higher spin generalization of the Miura-Soro vertex algebra. And it admits the free field realization by something called the Miura transformation, as I will explain. The construction goes as follows. There's a basic building block, which is called the Miura operator, Ri here. It's a linear combination of the formal differential operator, dz, and the ji. The ji is the alpha in J1 vertex algebra current, which satisfies this ji-jj OPE relation. And they don't talk to each other. So the subscript I enumerates how many copies you have. So in this case, I will take n of them. And they don't talk to each other because there's a chronicle delta. So in that sense, this is a free field realization of W algebra. So to realize this W algebra of GLN, you take n copies of them. So as you can see here, I take the products of them like this, from R1 to Rn, and you can just formally expand it in the decreasing orders of the differential operator. So the first term will be the trivial nth power of the dz, but in the subleading, there'll be the currents that's coming out as a coefficients of the differential operator from U1 to Un. So this UN, UI currents are completely expressed in terms of this free boson JIs. So by using this OPEs of the JIs, you can also, of course, compute the OPEs of the UIs, and they are satisfying the known OPE relations of the W algebra of GLN. So the point here I'm trying to raise here is that this construction is actually slightly better than just saying there's embedding into the tensor products of the free boson, or by just saying there's a free field realization, because this construction is very constructive in the sense that if you want the higher rank, you can just provide more factors of the Ri's to the left and just multiply consecutively to get the higher rank W algebra. So this structure should remind you about something that's very familiar in the integral model. So when you think about the spin chain system, for instance, there's something called a Lox matrix, and you take the products of them, and how many spin sites, depending on how many spin sites you have, you take as many as the number of the Lox matrices, and construct what's called the monodromy matrix, and that is the generating function of the quantum Hamiltonians of the spin chain. And what I'm doing here, extracting the UI current, is something similar to what's done in that setup. So algebraically speaking, the product of R matrices, so Lox matrices of the spin chain is certain R matrices of the quantum group. They decompose under the coproduct operation as a product. So this gives you a clue that Miura operator may be an R matrix of a certain quantum group. The second clue is more explicit. So this is by Malolio-Kunkov. So in the construction in the previous slide, the ordering of the Miura operator shouldn't matter in constructing which W algebra that you get. So you can swap, you have to be able to freely swap the ordering of the adjacent Miura operators. So as you can see here, I took the product of R1 and R2 in different orderings. But they have to generate the same Miura-Soro algebras. So what does the job is called the Malolio-Kunkov R matrix, which is called RMO here. So they are the same up to the conjugation of RMO from the left and right. But once I choose to write these Miura operators as R1 and R2, it suddenly looks like a Yang-Baxter equation. So it will be a Yang-Baxter equation, but for that, Ri should be the Miura operator should be an R matrix. So I will not exactly answer the exact question that I just raised. So there's good amount of understanding for this case too, but I will actually consider some Q deformation of it. And this actually connects to the previous talk by Go too, this Q deformation. So this Q deformation has to do in the following, in the physical setup. So as I said in the introduction, there will be some M-theory setup that everything is embedded. And in this M-theory, there's some choice of the complex two-dimensional manifold. And up to the, depending on which choice you make, the quantum group that you have to deal with changes. So in the case of C times C, it's going to be what's called the one-shifted affine Yang in of G1. For C times C star, it's going to be affine Yang in of G1. And for C star times C star, this is the case I'm considering. It's going to be quantum toroidal algebra of G1. But I'll get into the detail soon. So, okay, this is the outline. I'll first introduce the M-theory, twisted M-theory setup, and the 5D Chern-Simons theory that follows. And I'll introduce the branes inside and intersections of them, and how explain how these intersections lead to Miura operators. But and additionally, in the previous slide, there's a QQ character. And for a certain subset of the QQ characters that's associated with the D4 branes in the previous talk, this M-theory setup gives you a nice algebraic construction for those objects. Okay, so any questions so far? Let me begin by introducing the twisted M-theory that's initiated by Kevin Costello. It's an M-theory, so it's 11-dimensional. It has 11-dimensional wall volume, and the wall volume is R2 times R2 times R2 times R2 times C star times C star. So as I promised, there's a choice of there's a complex two-dimensional manifold, and I just wrote it as C star times C star here. And well, the metric is flat, so it's very simple. But I intentionally split this R7 into R2 times R2 times R2 times R, because I want to implement what's called the omega background. Omega background is can be thought of as turning on potential that respect to the rotations of these R2s. The subscripts or epsilons are the omega background parameters that controls the magnitude of this potential. So with this background, the preserved supercharge Q, epsilon 2, squares to not 0, but the isometry that's rotating these R2 planes. So I wrote down this the vector fields associated with the R2 rotations. Well, what implements this omega background, if you're interested, is the freeform background of the 11-dimensional theory. So when epsilon 1 and epsilon 2 are turned off, this R7 part turns out to be topological in the cohomological sense. And C star times C star turned out to be holomorphic. So it means the physics only depends on the holomorphic degrees of freedom here, and doesn't depend on the metric on R7. So in this sense, this theory is a holomorphic topological theory in the cohomological sense. But now I turn on the epsilon 1 and epsilon 2 and localizing the physics to the fixed points of the rotations of R2 planes. So since this is 6-dimensional R2 planes, so once you localize, you're left with the 5D effective physics on R times C star. Sorry, R times C star times C star. And this theory turns out to be what is called the 5D G1 Chern-Simons theory on this point word volume. So the effect of omega deformation is twofold. So one of the omega deformation parameter plays a role of the H bar parameter for this quantum field theory. And there's epsilon 2, the other omega deformation parameter, which controls the non-commutativity in the complex two-dimensional space. So this is the action of the 5D Chern-Simons theory. And as you can see, some part of the action resembles the usual Chern-Simons 3 form that defines the 3D Chern-Simons theory. But there are two additional features. It's provided with the holomorphic 2 form of the C star times C star. And there's the usual wedge product of the form deforms into non-commutative Moyer product. That's written here because of the non-commutativity. So what you can recognize here is that there was actually the triality of rotating this R2 plane, swapping these R2 planes. So in some sense, these epsilon parameters has to be symmetric. But once you get down to the 5D effective dynamics, this triality is similarly broken. The epsilon 1 and epsilon 2 seems to play a different role. But once you compute some quantities like vacuum expectation values, which doesn't break this symmetry, they have to be symmetric. The triality has to be recovered. Okay. Now I will introduce the branes in this setup. As we know, there are M2 branes and M5 branes. And because of the symmetry reason, M2 branes can only be supported on R2, one of the R2 planes, times R. And the M5 branes can be supported on two of the R2 planes and a holomorphic curve inside the C star times C star. So I parameterize the choice of the holomorphic curve by integer P and Q, which is given by this algebraic equation inside C star times C star. But for most purpose of the top, I will just choose 1, 0. So 1, 0 is just the X plane. I'll talk about the more general case in the later slides. But for now, we can just take this holomorphic curve as the C star X plane. So here, there are some examples for the M2 branes and M5 branes. As I said, M2 branes can occupy one of the R2 planes like this. The X marks are the support of these M2 branes. And they are supported on the same RT. On the other hand, M5 branes are supported on two of the R2 planes and X plane. So once localized to the 5D Chern-Simons theory on here, you can see that M2 branes always create a line defect along the RT, and M5 branes always give rise to holomorphic surface defects on C star plane. And so the most generic case would be the following. So you can have L, M, N amount of M2 branes in different orientations. I call that line defect L element. You can have capital M, capital N amount of M5 branes. I call that surface defect S element. Okay. Okay, so what about these surface defects and line defects? So let's think about the local operators supported on these defects. These dots, red dots on the line defect and the holomorphic surface defects. The point is that because on the line defect, these local operators can collide each other because the theory is topological along this R direction. And because of that, the space of local operators is endowed with the product structure. We have to say how they collide. When they collide, they define a new local operator. So in other words, there's a multiplication structure on the space of local operators. So the space of local operators becomes an associative algebra. And I call this associative algebra conveniently M2 element. On the other hand, when you have a surface defect, SLMN, now you can have the holomorphic position dependence of these local operators. Then when you try to collide, you have to specify the singular behavior of these local operators. In other words, you have to impose the OPEs of these local operators. And that's essentially what physicists call the chiral algebra. So I will call the mod algebra of this chiral algebra by M5 element. Any questions so far? M5 element. M2. Okay. So I didn't write it, but in the most generic case, I could have L, M, N amount of M2 branes, which are differently oriented in the R2 directions, but they are all occupying the same RT. That's why they create a single line defect in the 5D Chern-Simons theory, which I call L element. Similarly for the M5 branes. And I call the algebra that's living on this line defect M2 element. Whereas the vertex, there's a chiral algebra that's living on the surface defect. But I call the mod algebra this chiral algebra M5 element. So that's just the name, convenient names. The question would be then what these algebra are. I mean, they're just names. I didn't say anything about what they are. So the statement is the following. There's a constraint that they have to satisfy because this line defects and surface defect has to couple to the bulk 5e Chern-Simons theory in consistent way. What is a consistency? It's a gauge theory, so they have to be gauge invariant, the coupling. So the coupling, the gauge invariance of the coupling requires the algebra, this algebra of local operators to be images of certain universal associative algebra. So in the current case, where for the 5e Chern-Simons theory on R times C star times C star, the suggestion is the following. The suggestion is that this universal associative algebra is given by quantum toroidal algebra of Q1. You may not know what this algebra is, so let me give you an idea. So it's a certain Q1 deformation of the quantum torus algebra. The quantum torus algebra is nothing but the simple algebra generated by X and Z, satisfying this non-commutativity with the Q2 non-commutative parameter, but it's a further Q1 deformation of it. Right. So let me recap. So there, I said there's a universal associative algebra, and the M2 element, the associative algebra on the line defect, are the surjective images of the some map homomorphism. And similarly, for the mode algebra, M5 element, it has to be surjective images of some map from the quantum toroidal algebra. In principle, so this claim has to be verified within the perturbation theory of the 5e Chern-Simons theory. But to some technical problem, we couldn't do that. For the case of other cases like C times C star, it could have been done. But it could be done, but for the case of the C star times C star, we couldn't do that yet. It's an open problem, but I will provide an evidence that this statement is true by explicitly constructing some of these images M2 element and show that they admit the surjective map from the quantum toroidal algebra. Okay, so I'll go into the line defect M2 element, but let me start from the simplest case where L is non-zero, but M and N are 0. So you only have L amount of parallel M2 branes on top of each other. So they're wrapping this R2 epsilon 1 plane times R. So the idea is that you go to another duality frame and read off what this algebra M2 L00 is. It admits a 2A reduction to D2 D6 system. Because there's a top knot involved, there's an emergent D6 brane. And this LM2s become LD2s. And LD2s lie on top of 1D6. So it's exactly this Jordan quiver with the one self loop and the framing given by the D6 brane. So at epsilon 1 equals 0, there's an effective 3D n equals 4 theory that's living on this D2 branes, and which flows to the topological sigma model with the target space given by the Higgs branch of this quiver, this gauge theory. So it looks like the usual story, the Nakashima quiver variety, but there's a the difference is that there's a C star compact direction into the transverse directions of the D2s. So D2 open string can wrap around these compact circles. So that modifies the Higgs branch to be what's called the multiplicative quiver variety. And as you can see, this looks like a multiplicative uplift of the Nakashima quiver variety. So there's the linear map A and B got multiplicatively uplifted, and they satisfied this moment map equation. And by taking the quotient, there's this variety. So our sigma model has target space given by this variety. So now the algebra M2 L00, it's algebra of local operators of this sigma model. So this is nothing but the coordinate ring of this variety. So it's a commutative algebra of holomorphic functions on this variety. So now I want to turn on epsilon 1. So you can see that the Q2 appeared as in the definition of this variety. I didn't turn on epsilon 1 or Q1. Now I'm turning on, and that exactly non-commutatively deforms this ring of the coordinate ring on the variety. And the answer is no. So this answer, the ring that non-commutatively deformed this coordinate ring on this multiplicative variety is what is called the spherical Daha, spherical double affine Hecke algebra of type GLL. It's just the name, the spherical Daha. It is nothing but some algebra that's generated by the following difference operator, the Q difference operators. These are the generators, some polynomials and the difference operators in the polynomials and xi's. So in particular, in the case of the single M2 brane, this quantum torus, it reduces the quantum torus algebra. So it's certain generalization of the quantum torus algebra. So yeah, so the claim is that this spherical Daha of GLL is the M2L00. Okay, so and given that, how do I make I claim that there's a map from the universal associative algebra to this M2L00, and I claim that this universal associative algebra is quantum toroid algebra, and we already know the answer that from the quantum toroid algebra, there's a surjective algebra homomorphism to the spherical Daha of GLL at each L. So as you can see, in this sense, the quantum toroid algebra of GLL1 is large n limit of the M2 brane algebra and the spherical Daha. And also, it's known that the quantum toroid algebra is invariant under the exchange of the epsilon parameters or the exponentiated Q parameters. In this sense, it also meets the requirement that the twisted M-theory setup, there was a triality of swapping the R2 planes, and so that the universal algebra has to be symmetric under this exchange, and it meets the requirement that it's trially invariant. So it's a very natural guess that this indeed is on universal associative algebra in my setup. Okay. So now I'll introduce what the quantum toroid algebra is. The quantum toroid algebra is some algebra that's generated by these currents E, F, and K. These are the relations that satisfy these currents. And I don't think it's very intuitive to go over this definition line by line, but the only thing that you have to know is that they satisfy some non-commutative relations when the current exchanged with each other. There's some factors coming out here, and this factor is controlled by the Q parameter, and it's trially invariant by construction. Okay. So from the quantum toroid algebra, I can explicitly write down this map that I raised. From the E generators, the image is the P1K, and from the F, the image is the P minus 1K, and H generators go to the P0Rs. Okay. Any questions so far? Okay. So the quantum toroid algebra is not just an algebra, but it also has the co-algebra structure. So let's think about the local operators that's supported on the two line defects, parallel line defects. And let's imagine they are fused into a single line defect like this. So what would that mean? So that means that there's a local operator on the fused line defect. So it should be able to be decomposed into the local operators on individual line defects. So it means that there's algebra embedding of this L2 L plus F prime into the tensor products of M2 L00 and M2 L prime 00. And each of them, I claim, it receives the image, the surjective maps from the quantum toroidal algebra. So in this case, on the right-hand side, it receives the map from the quantum toroidal algebra, and then on the left-hand side, it should be from the tensor products of itself. But I can do this for any L's and any L primes. So there must be an algebra homomorphism from the quantum toroidal algebra to the tensor products of itself that makes this diagram commutative. So this notion is exactly the coproduct. There's a known coproduct for the quantum toroidal algebra, and so we can apply this coproduct to the spherical Dahas that I talked about, and it indeed makes this diagram commutative. So in that sense, it passes the consistency check. Okay, and we can go further. We can do for something more general. We can introduce now the M2 branes that's not oriented with each other. So in most general case, I have L M2 branes, M M2 branes, and N M2 branes that's wrapping the R2 epsilon 1, R2 epsilon 2, and then R2 epsilon 3. So that's the line defect L element. So using this coproduct, I can compose all of them into a single line defect, and the M2 element should be the image of this coproduct composed with individual individual maps. So we can compute it, and it produces new representation, new representation of the quantum toroidal algebra. And you can recognize some pieces are resembling the previous spherical Daha or McDonald operators, but now the Q's are appearing in some symmetric manner, and it becomes more complicated. Okay, so that was for the line defect. I'll go into the surface defect now. Is there any question? Okay. So now I'll go into the surface defect. So surface defect is created by the single M5 brane supported on R2 times C star. And by the 2A reduction, it becomes a single D4 brane supported on here. And so by Shipman and Vassaro, it's known that there's a the Hilbert space of this theory, single D4 theory, is known to admit some action of the quantum toroidal algebra GR1, and it is called the free Q boson algebra. So the natural gas suggestion is that the M5 100 or the single M5 brane corresponds to the free Q boson algebra. And this is the explicit map from the quantum toroidal algebra to the single free Q boson. So this Q boson satisfies this commutation relation here. The modes are called the ARs. And from these ARs, we construct certain vertex operators like eta, C, and phi. And the images of the E, F, K plus minus currents are written in terms of these vertex operators. And yeah, so this is an algebra homomorphism. Okay, so then what we can do is to stack up on top of each other like this and initiate the fusion as we did for the line defect. So that algebraically, that means that we map through the n-1 times the coproduct and further the individual maps to the free bosons. And we land on the M500. So this is exactly the setup that I started with. It's going to engineer the Q-deformed W algebra. That's then I can fuse them into S element. And in this case, I will get M5 element, not M500N. And this corresponds to the Q deformation of the Y algebra that's studied by Gaillot.
Sorry, in
Yep.
the previous slide, so what you get there is they produce the Q deforms the Miura transformation. So that's a statement. The formula looks more complicated than the Miura itself.
So I didn't introduce the Miura operator yet.
Okay.
All I'm saying here is that you start from individual free bosons on each of the surface defects. I want to go through this coproducts.
Yes, yes.
And then further this individual Q boson mass. That's the Q boson. That physically that's initiating fusion into a single line defect. So as a result, there's going to be some car algebra and a model algebra given by something that's going to be Q deformed W algebra.
Okay. Oh, I see.
But Miura operator hasn't been introduced.
Not yet. Twice.
This slide, the purpose is that now I vary orientation by parameters.
Yeah.
So in this case, I have the generalization of the Q deformed W algebra. It's called Q deformed Y algebra. Okay. For the R-matrix operator, now I have to deal with the situation where the surface and line defects coexist. So let's think about the configuration where line and surface defect are introduced on top of each other. So, so here's a line defect and there's a surface defect. They intersect at a point, and at the point, there will be a local operator supported on the intersection, which I call RC. Since it is supporting the line defect, I have to be able to construct this RC as an element of the tensor products of this line operator, line operator algebra M2001, and the border algebra of the surface defect vertex algebra, the M5. So the point is that I want to study the gauge invariance of this local operator. So that's done by drawing a small sphere around this local operator. So this gauge variation of this local operator turn out to receive contributions from the intersections with the line defects and surface defects. So there are three intersections here, North Pole and South Pole, and the circle on the surface. But the contribution for the surface decomposed into the two contributions in the language of the model algebra, because this is not the origin. So in total, there are four contributions from downward of the from upward direction, downward direction, and also the inward direction and the outward direction. And in terms of orientations of the line defect and surface defect, and they give such a contribution to the gauge variation. So it multiplies the local operator RC from the right in this way and this way, and there are four contributions. But it is only classical contributions, and there will be nonlinear corrections to this equation, gauge invariance, at the quantum level, and we postulate that this relation, this gauge invariance relation also respect the algebra structure. So the natural thing that generalizes this things in the parentheses is the coproduct again. So we postulate that quantum mechanically, the gauge invariance condition for RC is written in terms of the coproduct like this. So here, it's in fact the coproduct composed with, again, the M2001 and M5C. Okay, so this is one way to define the R matrix for the quantum group, in fact. So for a quantum group, there's a notion of the universal R matrix. So what's the universal R matrix? It is some object that lies in the tensor products of itself, and satisfying these three relations. So the first relation involves the coproduct, the coproduct of the element multiplied from right and left, and also some decomposition relation. So the first relation is nothing but the one that we have seen in the previous slide, but mapped it through the M2 tensor M5. So the claim here is that the RC that I wrote down is the R matrix between the two images of the quantum toroidal algebra. So this object, the universal R matrix for the quantum toroidal algebra, is somewhat well studied. It's known that it's written in terms of as a product of R bar and K, where K part involves only the Cartan part, in particular the HR modes, and the R bar part is expanded in some degree, in increasing degree. So the first term is identity times identity. The second term is EF tensor F minus K. But now in the sublimiting terms, there will be quadratic terms in E and K, but the generic expression is not known. And that's partially because we don't know which basis to expand this R matrix, universal R matrix. So if I want to start from given universal R matrix and map it through the M2 and M5 brane representation that I constructed in the previous slide, I can't do that. But what I do is actually the other way around. Even though I don't have the generic expression for the universal R matrix, I can just map it through and define this object RC and solve this constraint, the defining relation for RC that follows from the previous the equations. Then it's possible, and it boils down to this expression R bar times C, and the C part is explicitly written as some products of the vertex operator that involves the positive modes. And one thing to note is that x1 here plays the role of the argument of the vertex operator, but as you can see in this expression here, it lies in it is a generator of the quantum torus algebra. So the position of the vertex operator gets reinterpreted as a generator of the M2 brane algebra. Similarly, in the R bar, we can explicitly solve this object R bar here, and this is the solution. Again, it's written in terms of the vertex operator DC, and the argument is again given by the x1. X1 is again one of the generator of the M2001. So yeah, so this is some concrete R matrix of the quantum toroidal algebra. And in the case of the C equals 3, that means that the surface defect and line defect are totally transverse. This expression actually simplifies, and all the subleading terms truncates, vanishes, and all you left is the first order difference operator like this. So if you remind the first slide about the Miura operator, it was a first order differential equation, and this is a Q uplift of it, Q deformation of it, where the Miura operator for the Q deformed W algebra given by the first order difference equation. Sorry, the first order difference operator. But in general, it's more complicated because it doesn't truncate. The M grows up to infinity. Okay, so these are some R matrices. So if I visualize this on the picture like this, I can stack up this M5 branes on top of each other with varying orientations and line defect L001 passing through, and there will be R matrices from R1 to Rl plus M plus N. And by initiating fusion, they will be fused into single line defect where M5 LMN leaves, and there will be single R matrix between M2 and M5 LMN. So it means because of this fusion, under the coproduct operation, the full R matrix is decomposed as a product of individual basic R matrices like this. So this is exactly the product structure that we observed in the first slide. The product of Miura's operators giving the generating currents of the Q-deformed Wall algebra. Yeah, so yeah, we can decompose these products in increasing orders of the difference operator, and each coefficients can be extracted, and they generate the Q-deformed Wall algebra. So here we are talking about three different sets of the generator. So the first thing is what's generated by this R matrix, and second is the image of the coproducts, what we call the Q-deformed Wall algebra, and the third set will appear in the next slide. So so the problem is that the first set is definitely a subset of the second, but the question is whether they span all. Do they generate all? So whether the first set is equal to the second set is a problem, and we can show that with the help of the screening operator. So screening operator also appeared in the previous slide, and there's a construction of the screening operator also in this M-theory setup with the intersecting defects. And for that, I need to introduce the line defect that's ending on the surface defect now. So in this case is where the surface defect and the line defect are sharing some of the R2 planes in the topological part of the wall volume. Then they can end on the line defect can end on the surface defect, and there'll be a local operator that's supported on the line on the surface on the intersection. And by the similar reason, we can postulate that the gauge invariance condition for this object phi it can be written like this. Another way to view that is that there's a trivial line defect, which means there's nothing. There's no defect in the upward direction, and just write down the similar constraint that I wrote for the R matrix. But all we have to say is that trivial line defect is associated with what is called the co-unit of the quantum toroidal algebra, but it's just some unnecessary complication. So this equation, this constraint for phi, algebra in the quantum toroidal algebra literature, this is called the intertwiner of the quantum toroidal algebra. So we can do the opposite, and we can also think about the line defect ending from the above, and it will define certain object phi star that satisfy this constraint. And this intertwiners phi and phi star is obtained a long time ago by Feckin and others. It can be explicitly written in terms of the generators and the free boson modes in this way. So this is nothing new, but the point is that now we can think of fusing these different line defects ending from above and below, and in the case where the line defects are when the line defects are overlapping with some of the topological planes of the surface defect, we can split this configuration in like this. So it should mean that the R matrix that's supported on here should be decomposable into phi and phi star intertwiners, and by explicit computation, it can be confirmed. So this integral formula here, well, by the OPE of the phi and phi star, we pick up some Q Pohang symbol, and this contour integral picks up all the simple poles from the denominator, and we recover. It can be shown that we can recover the R matrix that I introduced earlier. So this equation is the visualization. This picture is the visualization of the equation below. Okay, so let me get into the screening charges that I wanted to say. So the screening charges are constructed by the M2 branes that's stretched in between two M5 branes. So so here there will be a phi star and phi, and there's a line defect that's stretched in between the surface defects, and there'll be local operator phi and phi star supported at the intersection. And if we define this object to be S, it will play a role of the screening operator. And so it's given by tensor products of phi and phi star. So these two cases are different by the orientations of the M phi branes. So here, this M phi brane and this M phi brane are parallel to each other. They're occupying the same topological planes, as the subscript suggests. And here they are different. So in this case, there's only a single M2 brane that can be stretched in between. But in any case, in this is two possibilities, and in both cases there will be some M2 branes that can be stretched in between with a finite length. So this object Sn, these screening currents can be explicitly written down like this. And now we can show that these screening currents are commuting with the images of the coproduct. And it's a simple argument. Only by only using the definition of the screening currents in terms of the intertwiner and the properties of the coproduct. So yeah. Okay, so what's the point? The point is that I have introduced three sets of generators. The one that's constructed by the R-matrix, the Miura operator, the images of coproduct, and what's commuting with the screening currents. There are three different sets. The claim is that they are all the same. The two inclusions, the first included in the two, second included in the third, is trivial. Or at least I introduced why these two inclusions hold. And there's a finite inclusion. The third one is included in the first. It can be also shown by explicitly solving for this the screening current. Just making an answer for the screening current that commute with what's produced from the Miura operator, and it can be shown that the third one is included in the first. So these three sets are all the same. So the Miura transformation indeed generates all the generators for the Q-deformed Y algebra, M5 element. So yeah, let me repeat. So the conclusion is that Miura transformation constructed by the R-matrices generate the whole Q-deformed Y algebra, M5 element. And also, the Q-deformed Y algebra is completely characterized as a commutance of the screening charges in the tensor products of Q bosons. Okay, so in the remaining 1 or 2 minutes, I will just skip this. I will say something about the QQ character that appeared in the previous slide. So far, I've only considered the surface defect that's occupying the X plane in the holomorphic plane and the line defect passing through. But this configuration can be more general. I can introduce more surface defects that's occupying different complex holomorphic curves inside C star times C star. So what are they? What's the meaning of them? And in particular, one of these configurations will construct the QQ characters for the Q-deformed W algebra. So as I said, when I introduced the M5 branes, M5 branes can be supported on generic holomorphic curve CPQ. P and Q parameterize which curve it is supported on. And so we can think of the reparameterization of the C star times C star by some SL2Z group. So SL2Z acts on coordinate X and Z in this way. Okay, so in other words, we can start from X plane, let's say, and apply this SL2Z transformation to get another CPQ holomorphic curve. And in the algebra side, the combinatorial algebra GL1. Indeed, admits the XL2Z automorphism group. So the idea is the following: we can start from the given Q boson algebra for a single M5 and just act this XL2Z to Z to construct the other algebras that corresponds to the M5 branes oriented in different ways. I mean, supported on different holomorphic curves. So for the T transformations, we can directly do this, and it looks almost the same. It's again expressed in terms of the vertex operators, but there's some additional some minor corrections by some these factors, by some x to the power of plus minus n. The S transformation is non-trivial, so and in fact, this Q-free boson is the one that's constructed by Fagin and Zimbaliuk, Shipman and Bassero. So let's think about the Q boson module as being defined on the space of Young diagrams. So the basis vectors are the Young diagrams, and in terms of on this basis, this EFK generators are represented in this way, and well, I know this definition is a little bit technical, but this is the one that's S dual. This is the image of the S transformation for the free boson that I introduced earlier. So now, when we have these intersecting holomorphic surface defects, it's very difficult to visualize because we are talking about holomorphic curves in C star times C star, and also there's an R direction. We can visualize the phi-dimensional theory. So it's convenient to go to the type 2 to be dual frame, where M2 brane becomes M33 branes and M5 branes on the curve CPQ become PQ5 branes. And some of you may be familiar with this setting. So the ones that's supported on the X plane, they become NS5 branes. And in general, the PQ5 branes become the M5 brane that's supported on the CPQ becomes the PQ5 brane. The M2 branes, they always become the D3 branes. Okay, so now we can visualize this PQ web and the D3 brane that's passing through in this three-dimensional space, RT, RX, RZ. It's three-dimensional space, so we can draw it. So when surface defect intersect, they make this kind of junction, and the PQ charge has to be preserved. So, but by the same reasoning that I introduced the intertwiners for the M2 M5 intersection, here M5s are intersecting with each other, but there will be some intertwiner of the quantum toroid algebra, psi and psi star, that's intertwining these different Q bosons with each other. So with yeah, this is the explicit expression for the psi and psi star. Again, very technical, but there is such an object. It's known from Awata, Fagin, and Shiraishi. Now the point is that you can compose them together. So on the left-hand side, you have the PQ web, but in the precise the same picture, why I associate the intertwiners of the quantum toroid algebra. And the point is that here I can compose this intertwiner as a map along this finite length and fibrils. So I compose this object T here and compute the vacuum expectation value. So I provide a vacuum, and it computes certain amplitudes in purely algebraic terms. So the claim is that this computes this is identified with the partition function of the phi n equals 1 gauge theory. And this is one way I can relate BPS counting to this setup. So let me remind you a bit of a story. So this for the PQ web, there's a toric toric, non-compact toric Calabi-Yau freefall, where the toric diagram is the dual graph of this PQ web, and there's a refined BPS invariance, refined BPS partition function, which is exactly matching with this partition function of the 5 equals 1 gauge theory in this 2B picture. But at the same time, there has been work that reconstruct this partition function in terms of the intertwiners of the quantum two-layer algebra tier 1. I think the first work was exactly Awata, Feg, and Shiraishi. And there were a lot of many follow works that generalizes the construction. But I think, as far as I know, there was no good physical reason why it has to be reconstructed in that way, why it has to be involving the representation theory of the quantum two-layer algebra. And I'm telling you, this gives one answer why you have to be able to recover this partition function from the intertwiners of the quantum two-layer algebra. The left-hand side, which is the web of this T object, the intertwiners, is nothing but the web of the intersecting holomorphic surface defects in the 5e Chern-Simons theory. So we're talking about some duality that relates 5e Chern-Simons theory with some 5e n equals 1 theory, or the M theory on compactifying on the toric Calabi-Yau. So yeah, that's one thing that's related to BPS counting, because this workshop is about BPS counting. We can do further. So I promised you I will talk about QQ character. So QQ character is the following object. I insert the D3 brane on top of it, or M2 brane on top of it, that passes through this PQ web. And algebraically, I introduce this M2 brane passing through as an R matrix of the quantum two-layer algebra. So this operation should correspond to inserting this R matrix of the quantum two-layer algebra between M2 and M5 in between this two sets of the intertwiners. So this is something very explicit. You can compute this map from the tensor products of from the tensor products of the Q boson to Q boson, and from tensor with the M2001, and compute the VAV in the sense that you provide some states from the infinity. So still I provide vacuum for the Q bosons, but I provide some ith state and I plus kth state and call it kth QQ character. True. I can do that. Yes. There's no reason why I should insert it in the middle. I can insert it here or here.
I see. Then you get the same answer, and then
yes.
And does statement is guaranteed by some consistency of the algebra? Like, how do you see that?
How do you see that?
Case by case or a general reason? That's what I'm curious.
No, I think it's by general reasoning. I don't know exactly how I should argue, but let me think. Because it's I'm talking about passing through R matrix through the intertwiners.
Yes.
But I think there's a way to argue this, but okay. It's actually important. So I'm able to insert it here or here. That tells me that I can expand this object in U or U inverse. So it becomes a one polynomial. It doesn't have a pole at in system. And that's one crucial property of the QQ character. Saebyeok, how long do you? Yeah. Oh, so my time is done. Yeah. So that was the point. So this computation can be explicitly done. It exactly refers the non-QQ character expression for the W algebra, and we can directly study from the Feynman diagrams in the 5e Chern-Simons theory. And the ultimate goal of the project that I want to study is that there's the problem of the quantum integrability of the moduli space of Higgs bundles that's associated with 4D n equals 2 and 5E n equals 1 theory. But now it's like we are decomposing the contents of the 4D and 5E theory into building blocks with these R-matrices, M2 branes intersecting with each other, and each of the intersections involved with the R-matrices. So of course, R-matrices have to do with the quantum integrability. So there must be a way to rephrase this quantum integrability from the R-matrices of the big quantum algebra, like quantum-Toric algebra of affine Yang. So that's the final goal. Thank you for listening, and that's all.
Any quick questions? Yeah. So the M2 algebra is just a vector.
I'm sorry?
The M2 algebra is just a vector.
I introduced only the vector, but it actually can be anything. So the generalization of the vector, which is quantum torus algebra, is the spherical Daha. And I can further generalize it by stacking up these spherical Dahas with different orientations. And that's what I call the generalized McDonald representation.
I see. So I mean, the interpoint that you constructed, like between each and E5
True,
is
true.
The one
Right.
you go as into is the
True. So the statement should be that you compose them together to get more interpointers between more complicated M2 brane with the surface defect. But it can be done.
I think also you constructed an R matrix where you have different types of G5.
Of course. Yes.
You can also do that.
Of course. So we will give the hierarchical characters.
And also another reason, so it's related to what you said maybe last part when you said at that time the next page. Please. Again,
Please.
yes, this one here. So you said that you can think of intersecting points of the X and again what, and you have it's like AGT. So in sense, what's the AGT you'll
Can you say it again?
So we have two corner vertex operator algebras. What is the AGT?
Right. So, well, we know how to compute the gauge origami partition functions.
Yeah. But it's not the point of view. Gauge origami construction of spiking stuff is like 48. So that one there's pures.
I mean, so we can compute the amplitudes of such intersecting surface and line defects in any configuration like this, and it should be compared with the gauge origami partition functions. Here I'm talking about only the M5 branes that's parallel to each other because I'm talking about, well, here it's I'm realizing the 5 equals 1 thing, but in principle you can have non-parallel M5 branes on top of each other. But
Yes.
that we know also
Geometry.
Huh?
Geometry.
geometry.
Yes. So in the 5D, so the usual spiking stuff is like C4.
Yeah. So there's a duality. There's a duality between this spiked Saturn configuration with the twisted M theory. At least you preserve. So you have to specialize the gauge origami setup because you have the Q1, Q2, Q3 independent there. You make unrefinement that Q4 is 1 or something, and you TDLize because that was a type 2B, and then you uplifted the M theory, and that becomes the twisted M theory.
So you can also do it when you have different types of M5.
Of course. But again, as I asked in your talk, one mystery is how to turn on the Q3. I don't think there's a good understanding of the turning on Q3 in the twisted M theory setup.
Yeah, no questions. Let's take Saebyeok again to the next.